All right, hello everyone, welcome. In this explainer, we are going to tackle carbon compounds. My goal? To help you master the naming system so you can absolutely crush it on your SPM chemistry exam.
Yeah, does this feel familiar? So many names, so many rules, where do I even begin? Look, I get it. It's probably one of the biggest headaches for chemistry students. But don't worry, today we're cracking that code. Together.
Okay, but before we jump right in, I want to give you a powerful tool to make all of this stick. Go ahead and scan this QR code or just type in mcqspm.com. Why? Because you can practice everything, and I mean everything, we talk about today on actual past year SPM questions. Seriously, doing the questions is the secret sauce. It's how you really learn.
All right, let's kick things off with a concept that you are almost guaranteed to see on your exam, isomers. Now, a super common mistake is thinking isomers are just totally different molecules. Let's clear that confusion up right now.
So, what exactly is structural isomerism? Think about it like this. You've got a box of Lego bricks. You can use those exact same pieces to build a car, or a house, or maybe a little spaceship, right? It's the same idea in chemistry. You have the same molecular formula, that's your set of bricks, but you can snap them together in different ways to build totally different structures.
And when it comes to your exams, you'll mainly see two types: chain isomerism and position isomerism. Let's stick with our building analogy. Chain isomerism, that's like tearing down the house and building a new one with a completely different layout, maybe a ranch style instead of a two-story. But position isomerism, that's way simpler. You keep the same house, but you just move the front door from the front to the side.
And here's a perfect picture of that. This is position isomerism in action. See that little OH group? It's just hopped from the first carbon over to the second one. The main carbon chain, the street, is exactly the same. All that's changed is the house number.
Now look at this. This is chain isomerism. The whole carbon skeleton has been rearranged. It went from a straight line to this branched T shape. So here's the absolute key takeaway. The formula, C4H9OH, is identical for both, but the shapes, totally different. Spotting this difference is a huge point scorer in exams.
Okay, so we get what isomers are. Now, how do we name them? This is where the IUPAC system comes in. I know, it looks intimidating with all its rules, but trust me, it's really just like a super specific postal address for every single molecule. Once you learn the system, you'll know exactly where everything belongs. And every single one of these addresses has three simple parts. First, the prefix. That's kind of like the house number. It tells you about any branches. Then you have the route name. That's the street name. It tells you how long the main carbon chain is. And finally, the suffix. That's like the city. It tells you what family the molecule belongs to. Get these three parts down, and you're golden.
Okay, let's put it into practice with this molecule here. Step 1. Find the longest carbon chain. But here's the catch, it has to include the important feature, which in this case is that triple bond. So, we count them up, 1, 2, 3, 4 carbons. 4 carbons means our root name is but. Step 2 is numbering that chain. And listen up, because this is where so many students lose marks. You have to number it to give the special feature, that functional group, the lowest possible number. So we're going to start from the right side, closest to the triple bond. That puts the triple bond on carbon number 1. And that gives us our suffix, 1-wine. All right, last step. Do we have any branches hanging off the main chain? Yep, we do. Right there on carbon number 3, there's a little methyl group. So that's our prefix, 3-methyl. And now we just assemble the name. We put it all together, and we get 3-methyl-but-1-9. See, it's a system, a logical one. Prefix, root, and suffix. Done. Okay, theory is one thing, but let's see how this plays out in real SPM questions. Once you start seeing the patterns in the exam, your confidence is just going to skyrocket. Here's a classic for you. I can almost guarantee you'll see a question about esters. The examiners just love to ask where they come from. So take a look at this one. How is this compound produced? Want the fast way to solve this every time? Here's the trick. Find that ester link, that COC bit, and mentally chop it right after the single bonded oxygen. The side with the double bonded oxygen, that always comes from the carboxylic acid. In this case, that's butanoic acid. And the other piece, that comes from the alcohol, which is ethanol. It's a super quick trick to work backwards and find what you started with.
And here's another exam favorite, identifying isomers. Just remember our Lego rule. You are looking for something with the exact same molecular formula but a different structure.
So your first step is always to carefully count up all the carbons and all the hydrogens.
So for this one, the answer is 2,2-dimethylpropane. Why? Well, if you count them up, it has 5 carbons and 12 hydrogens. Pentane also has 5 carbons and 12 hydrogens. The formula C5H12 is exactly the same. The only difference is one's a straight chain and the other is this more compact branched molecule.
So you might be thinking, okay, great for my exam, but why does any of this matter? Well, it matters because this stuff is literally everywhere you look. It's in the fuel that runs your family's car, it's in the gas you cook with, and it's even in the flavor of your favorite foods. This is not just theory.
You know that amazing fruity smell you get from certain snacks or drinks? Guess what? That's esters. And the cool part is, their very specific structure, the ones you now know how to name, is what gives them their unique scent. So, ethyl butanoate smells like pineapple. But if you just tweak that structure a little bit, you get the smell of a banana or an apple. It's all about the shape of the molecule.
And what about fuels? Well, the key thing here is that all that energy is packed into the chemical bonds, mostly between carbon and hydrogen. Because alkanes and alcohols have these simple, stable structures, when you burn them, those bonds break and release a ton of heat. And that heat, that's what powers our lighters, our cooking gas, and even our cars. So think about what you've just learned. You now know the basic rules for how these incredible molecules are built and how they get their names. This is the foundation, the key that unlocks the much bigger, more complex chemical world that's all around us. And please don't forget to keep practicing over at MCQ SPM. The more questions you do, the more all of this will just become second nature. So I'll leave you with this. The next time you smell a ripe pineapple or see a gas stove turn on, are you going to think a little differently about the amazing world of carbon compounds? Thanks so much for joining me for this explainer.